Don't forget to subscribe and ring that bell.
I see you there. I see you there back for the 2018 AP Calculus AB exam that College Board put out a little while ago. And we are going to continue Section 2, Part B. We are going to do free response question number 4. We do not get a calculator. Oh, poop. But that's all right. We can handle this. All right. Let's get started. I think we're in for a good one today. I do. I really do. So here we go. First of all, you know how I feel about graphs and tables and charts. Oh my, I love them. I love when they give me these things. I love visualizing things, and when they draw it for me, even better. 4 says, let f be the function defined by f of x equals 6 over 1 plus x squared. Let r be the shaded region bounded by the graph of f and the horizontal line y equals 3, as shown in the figure above. Find the area of R. Okay. First of all, let's note that we have 2 functions here. We have f of x, and then we have y equals 3. Now, without a calculator, Visca, how am I going to do this? First of all, y equals 3 is a horizontal line right at 3. This is the equation y equals 3, but you should have known that already. And that means this is f of x, 6 over 1 plus x squared. That is f of x, which is 6 over 1 plus x squared. And our lovely region R is right here in between them. Okay, find the area. Area under the curve. Okay, so we'll start this up here. I'm going to circle this, the area of R. Area under the curve just means we're integrating. All right, and what's even better about this is they give us, all right, they give us the 2 points of intersections. We can see them. If you want to check it algebraically, you absolutely can. I can set, well, I guess let me do this first. From -1 to +1. Those are our bounds. If I wanted to check that, I'm going to do this quick. Okay, I would set my equations equal. 6 over 1 plus x squared equals 3. Well, I know 6 over 2 equals 3. So the bottom has to equal 2. What makes 1 plus x squared equal to 2? I'll make that a 2. Well, if I put a 1 here, but I could put a +1 or a -1 in here because squaring it will make it positive anyways. So 1 plus 1 is 2. That means the bottom is 2. 6 divided by 2 is 3. Look at all that fancy work there. Okay, so you could check that algebraically if you wanted to. But that's not the important part here. The important part here is I need to find that area under the curve. Whenever I have 2 lines, 2 curves, 2 functions that I'm finding the area in between, it is always, always, always the bigger function minus the smaller function. We're going to integrate that. Okay? So the question is, what is the bigger function? The bigger function is the higher or the taller function. Okay, that's a function that's further away from the x-axis. And if I just concentrate on this area right here, okay, obviously the taller is the green, my f of x. Okay, so when I integrate this, I'm going to integrate f of x minus 3. Remember, my smaller function is just y equals 3. This is my bigger function. This is the smaller function. All right, so it's f of x minus 3. Don't forget your dummy variable dx. So I'm going to take that, I'm going to bring it down below, and we're going to do all this work. It's going to be a little bit of work because I noticed something right away, and I will share that with you in a moment. So let's scroll down here, and let's write our function properly. The integration of f of x, which is 6, over 1 plus x squared minus 3, this whole thing dx. Okay, and I want that from -1 to 1. Let's not forget our bounds. Okay, so what I noticed right away is the following. Let's extend this to give ourselves some room, because guess what? We're going to need some room here, kids. This right here, before I integrate, I'm going to break that up. I'm going to integrate, okay, 6 times 1 over 1 plus x squared. And then I'm all, minus 3, okay? But keep in mind, I can integrate these separate if I want. I could just, integration from -1 to 1 of both. I could do it like this if I wanted to, okay? I don't have to. I know some people get crazy about wanting to break them up, which is fine, but I'm just going to keep them like this for now, all right? And let's get this bad boy out of here. Just a little dot. Gone. Man, he really went into the stratosphere. Okay, so this is what we got. And what's so, I don't want to say important, but what's so crazy about this right here? It's the following, okay? First of all, this is multiplication. We're just going to pull this out. So it's 6 times the integration, all right, of 1 over 1 plus x squared dx. I am going to split this up so I can pull that 6 out. Minus, because this 6 isn't going to be multiplied by the 3, so that's going to be its own separate, from -1 to 1, integration of 3. This right here, that is a rule. That is a trigonometry rule. If you forgot, let me remind y'all that the derivative, there is a derivative of something that when I take it, it's 1 over 1 plus x squared, and that is the inverse of tan. Okay, that is the inverse of tan. So if the derivative is going this way, I have this, I'm going back, that's the integration. All right, so let's just go ahead and integrate that right now. Okay, I've got 6. This becomes tan inverse of x from -1 to 1, okay? Minus, okay, oh, look at us. We forgot our dx right here. So naughty. We are so naughty. Okay, we're subtracting. I integrate 3, comes 3x from -1 to 1. That's what we have right now in front of us. That is not horrible, I guess I should say. That's not horrible at all. But keep in mind, you guys are going to, you're going to have to know your angles, or I should say radians for tangent. Okay, we're going to have to know these things to solve this. And when we talk about radians, there's that black dot again. We talk about radians, we're talking about bringing pi into the equation. Okay, so we have green 6 times the tan inverse of 1 minus the tan inverse of -1 minus 3 to the 1 minus 3 to the -1. Yeah, this is easy. It's 3, that's plus 3. I'm subtracting, so it's -6 here. All right, that's the right side. That's the cake work. Here I've got 6 times. Okay, well, I know the tangent of 45 degrees is 1. Okay, but in terms of radians, that's pi over 4. Okay, if converting degrees of radians gives you issues, I suggest you practice it. And you start by knowing that pi is always equal to 180 degrees. And I know if I divide pi by 4, that's going to give me 45 degrees. So if I divide 180 by 4, I got to divide pi by 4. Okay? But you always start with the fact that pi is 180 degrees. Okay. Good. Good, good, good. Here we go. So minus, all right, now what's The tan of -1. Hmm. 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 This is where it helps to know your graph of tangents. This is where it helps to know your graph of tangent. Yeah, you could use the unit circle, but I like using the graph of tangent slightly better. Let's go here. We have the graph of tangent. I'm going to graph it right here. Here's 90 degrees, or pi over 2. Okay, here's -90 degrees, or negative pi over 2. All right? I know that there are asymptotes here for tangent. And I know the graph of tangent kind of starts here and goes up like this, and then it just kind of goes down like this. Right? Tangent is equal to 1 at this point, which is pi over 4, which is our 45 degrees. It's equal to -1 at this point, which is negative pi over 4. Okay, it's just in the opposite direction. Okay, so on your unit circle, what would that be? 315 degrees? It would be. But 315 degrees is -45 degrees. I would rather work with smaller numbers. So I'm just going to say that's -45 degrees instead of 315 degrees. If I know 45 is pi over 4, -45 is negative pi over 4. Okay. So now we've got this whole thing right here that we got to kind of solve. It's not solved yet. We just got to simplify this. It's a lot of work. It's a bigger integral to set up because we have two functions. There's tan inverse we got to bring in. We got to know the values of tan. We got to know how to convert those degrees to radians. And then we got to simplify. This is a rigorous problem, so to speak. Okay, so let's do this here. Subtracting a negative is kind of like adding. Okay, and if I have pi over 4 plus pi over 4, it's 2 pi over 4, which is the same as pi over 2 if I reduce it. But then I'm going to multiply it times 6, right? Don't forget about 6. Okay? Now, that 6 is just hanging out there in between both of those. I promised to myself that I was going to make this look a little nicer. So here we go. So 6, and don't forget we still have this -6 up here. Okay, we can't forget about that. That -6 comes for the ride. So I know that 2 goes into 6 3 times. So I have 3 times pi minus 6. This right here is the simplest version of the area between the curves f of x and y equals 3. That area of the region R is 3 pi minus 6. That was it's a pretty good problem. It's a pretty tough problem. It challenges you on many levels. Every time you get a question like 4b, you should be so thankful. It says, write, but do not evaluate an integral expression for the volume of the solid generated by R when R is rotated about the horizontal line, y equals 7. Write, but do not evaluate. You got to set up an expression to solve it, but then you don't have to solve it. That saves you so much work. So really, this is testing you on how you know how to set up a problem to solve, obviously. Okay? And I've got my graph here. What I'm going to do is, because I have the y equals 7, I'm going to kind of make this a little bit smaller here. That's good. All right. So here's our original function f of x. Okay? We'll still do this here. F of x was in green, so I'm just out of memory. If you saw part A, you know what I'm talking about. If you didn't, that's what I'm doing. This is f of x. I'm going to do this red. This is y equals 3. Okay. But they give us this line, y equals 7. So here's where y is 7. Okay. And they want this shaded region R. Let me get the crayon out of here. What the heck's that crayon doing? Well, the shaded region R to rotate around y equals 7. And they want the volume of the shape that's created when that gets rotated. Meaning, okay, I'm rotating around y equals 7. Okay, which means y equals 3, that's 4 away, so it's 8, 9, 10, 11. If I were to continue this, okay, this y equals 3 would rotate and go, I'll do that in gray because it looks like kind of like a shadow. Okay, and then this graph, this curvy green one, kind of goes like that. So that region is also going to kind of rotate over here, R, when it rotates, and it will go spin like back around here and back, okay? So that's what we're doing. Now, volume. Anytime I integrate volume, anytime I integrate volume, it's area. I've got to integrate area. In this case, I'm spinning it. You can kind of see this circle. I don't know if you can see this. I'm going to do this in a thicker, let's do this in a nice light blue. This is going to end up forming like a circle when I spin it. Okay, it's a little stretched out. It's going to be a circle. So my area is really pi r squared. This is the area of that shape that's going to kind of make a circle for us. I want to integrate, okay, volume is always when I integrate the area, okay? But the question is, okay, pi, the area is pi r squared. My pi I'm going to put outside. Okay, so I'm going to integrate pi. The bounds are still the same. Okay, if you didn't watch 4a, the bounds were from -1 to 1. Okay, so I got -1 to 1. So I go -1 to 1. My radius is what I don't know. I'm going to put parentheses there and I'm going to square it. And my dummy variable dx. Okay, so what? Okay, the radius is going to be, again, it's bigger minus smaller. So what we're really doing here, and let me clean this up, is we're really going to have, I said we're going to have a big circle here. We're really going to have two circles. There's going to be a big circle on the outside formed by when y equals 3 is rotated. Okay, and I think what I'm going to do is I'm going to kind of try and redraw this so it's nice and fancy. Okay. In red is going to be my big circle. So my big circle is going to go from the top here, come down. That's what happens when I spin y equals 3 around 7. But notice there's that gap. This gap from here to here should be empty. So I'm going to subtract the small circle that this makes, okay? Because everything else is going to be solid fill. This is going to be the solid fill I get when I take the small circle out of the big circle, okay? So really, the area that I'm finding, or the volume of the shape I'm finding, the area that I'm integrating is all this stuff right here. Okay, I hope that makes more sense to you. So in order to find volume, I integrate the area. I've got to integrate the area of the big circle and subtract the integration of the smaller circle. Okay, I don't know any other way how to say it besides just like that. Okay, so my radius, okay, I'm really going to do this in one integral instead of two. I could do two separate integrals, but I'm going to do it in one. It's the bigger radius minus the smaller radius. They're both going to be squared. They're both going to be multiplied times pi. Okay, so we're good. It's the bigger minus the smaller, just like 4a was. Okay, the bigger one is the one that's furthest away from 7. Okay, y equals 3 is farther away than f of x. Okay, so I'm going to take 7 and I'm going to subtract 3. That's the bigger radius. I mean, doesn't that, we're at 7. We take away 3. It should be 4. The radius is 4. Okay. So it's 7 minus 3. Now I've got to subtract, okay, 7 minus whatever f of x is. If you want to write 1, it was 6 over 1 plus x squared. I mean, if you want to write that, you can. You don't have to. There you go. Okay? How come, the million-dollar question is, how come I write 7 minus 3, not 3 minus 7? Or why don't I write 11 minus 7 and 11? Here you go. I'm going to erase all this drawing right here, okay, on the graph. When I started with this thing, just to let you guys know, this is what I started with. And this one right here was y equals 7. This is what I'm starting with. Isn't 7 bigger than both of these functions, f of x and 3? Because it's taller. It's further away from the y-axis. So that's how I know this is bigger. That's how I know I'm going to start with 7 and subtract 3 here. That's how I know I'm going to start with 7 and subtract f of x here. Okay, we're done. What I'm telling you now is just explanation, further explanation. They said write, but don't evaluate. Here, I wrote it. I don't want to evaluate that thing, not unless I have to. I mean, why would I want to? I mean, I want to. I'm a calc teacher. I love it. But there you go. That's your answer. We're done. All right. 4C. And I think problem 4 only has an A, B, and C. There is no D, so we are done after this. C reads, let h of x be the vertical distance between the point x, fx, and the horizontal line y equals 3. Find the rate of change of h of x with respect to x at x equals 2. Okay, let's establish what they've given us, because I think there could be a little bit of confusion here when you first read this. Okay, we know that this is f of x, okay? And we know that this is the horizontal line, y equals 3. Okay, let h of x be the vertical distance. So h of x is the vertical distance between a point x, f of x. When they say this, the fact that the y value is f of x just means, okay, it's some point anywhere on f of x. Okay, and if a y value is f of x, it's the function f of x. Okay, so that is now established. Okay, that you should know. Well, you should know to solve this problem. Okay, so this is really just saying f of x and the horizontal y equals 3. If I want the distance between the two, I've got to subtract them, the difference. Okay, the distance between these is the difference. All right, if this is at 6, okay, if this is at we got 6 and this is at 3, that distance is a distance of 3, isn't it? So I got to subtract them. So what I'm going to do is I'm going to say, well, I'm going to start with my y equals 3, and it depends where my point is on the f function. Meaning, if I got this point right here, okay, the distance from there is obviously different than the distance from that blue point to y equals 3. This one. So y equals 3 is the constant. F of x is what might change. So I'm going to start with what I know is a constant, meaning 3. So h of x is going to be, well, 3 minus wherever f of x point is. All right? And in this case, based on what they gave us earlier in the very first part for A, that's 6 over 1 plus x squared. That's h of x. Okay? That's the first thing that you need to be able to set up. Okay? Now, let's go back to the problem where it's, you know, the wording of the problem and understand a basic phrase in calculus. Find the rate of change of h of x with respect to x at x equals 2. God, I can't believe this is like a part C. It should have been a part A. Because rate of change is really slope. And slope as us calculus people lovingly like to refer it to, means derivative of h. So it's really h prime, where? At x equals 2. So this is what we're trying to find. We have h. Let's take the derivative of h, then plug a 2 in for x. Perfect. All right, let's go blue here. H prime of x is the derivative of a constant is 0. You don't have to write that, but I just did. Minus quotient rule. Quotient rule. Okay? Some people like to bring that bottom up and make it a -1 exponent and use the product rule. I had a student teacher who did that, and you know what? I mean, it worked for him every single time. But I like the quotient rule. Okay? This is my low part. This is my high part. Okay? I know it's numerator and denominator, but I always say this phrase that I learned in college that I teach my students, and it rhymes. Okay? It is low d high minus high d low. I draw a line and I square below. Okay, it rhymes. Low d high minus high d low. Draw a line, square below. Okay, so my low, which is my denominator, is 1 plus x squared. D high, that's the derivative of the numerator. D high. The derivative of 6 is 0. Oh, that's nice. That's going to go bye-bye. Minus high, which is 6. D low, the derivative of 1 plus x squared is just 2x. I draw my line, which is right here, and I square what, 1 plus x squared, whatever is below. I square this, and that's it. Okay, so if I want to at this point, I can just throw a 2 in for x. But since I got some zeros in there, let me get rid of that first. Let me clean this up a little bit. I always tell my students, that's weird. I was hitting the black thing and it just scrolled up. We're getting new smart boards, which is going to be nice. Okay, this 0 goes bye-bye. Okay, this 0, and I know I told you I tell my students something. I'm going to tell you in a moment. This 0 makes this go bye-bye. All right. So what I end up having is, okay, I have this negative sign. Don't forget that. And then I have this, which ends up being minus 12x. I can do 6 times 2 in my head. That's 12x, over 1 plus x squared. This is h prime of x. Let's figure this out at x equals 2. Now, what I tell my students is, if you ever have to find the derivative at a point, in this case, it's at a location of x equals 2, simplifying, they only make mistakes when they simplify. I tell them, if you have the quotient rule, do the quotient rule out completely, then throw the x in. Don't try and, simplify and make a mistake. But in this case, when I said I'm going to simplify it, I'm just really getting rid of the zeros, and I'm multiplying 6 times 2. Okay? So I'm not doing anything strenuous. All right, so let's throw our 2 in, and let's get our answer, and let's hightail it out of here, because you know what? I need to get some coffee. All right, let's go here. Let's go with this nice purple again. So it's negative 12 times an x, which is 2, all over 1 plus 2 squared. But this whole thing is squared, okay? Because the 2 is squared, then the whole thing is squared. Okay, don't forget one of those squares. So the top is negative 24 over the bottom. Well, you know what? I lied. The top isn't negative 24. I said we got to remember this minus sign, right? And I put it here. But then I said I have negative 12, and I didn't include this minus sign, which should be here. So you're subtracting a negative, which is going to make it positive. Let me say that one more time. This minus sign was this one, okay? Then I'll do the other one in blue. When I was supposed to write the minus sign that was here, I didn't. So there it is, minus. When I subtract a negative, it's a positive. That should be positive, which means this should be positive. Okay, sorry about that. Bam. And the bottom, 2 squared is 4. 4 plus 1 is 5. 5 squared is 25. All right, that's it. My answer is 24 out of 25. At the point where x equals 2. Okay, I want to say one more thing, which is very relevant. You may still have a question. Okay, at the point where x equals 2. When I set up this initially, right here, I started with a 3. And I said, well, I'm starting with the 3 because that's the constant. F of x may change, okay, but wherever that location is, but y is always 3. That's why I put the 3 first. Something that might make a little bit more common sense, why did I start with a 3 first? Where x is 2, which function is bigger? The further function away is 3. F of x is smaller. Okay, it's down here. That's why we always do bigger minus the smaller. So that might be a better indication of why we use 3 first. So it's 3 minus whatever f of x was, because 3 is actually the bigger function at x equals 2 than f of x is. Okay? Well, look at that. You know what? We're done. We spent a lot of time, about 30 minutes, going over 3 parts, but there was a lot of explanation. And you know what? I don't mind wasting that time as long as you get the material and you understand it, because that's why I do this. That, and I like to hear myself talk. I'm really a funny guy outside of math, really, kind of, somewhat. 4 people have told me that in my 40 years of living. 4. 1 a decade. That's really not a lot of people, but I think I'm funny. And you know what? I don't care if you think I'm funny or not. I care if you understand this math. I will see you later when we do problem 5. See ya.
Don't forget to subscribe and ring that bell.